All right, so today what we're going to do is we're going to talk about how do we use equations. Now, back when we were learning about equations and how to balance them, I kept on saying time and again, oh yeah, by the way, an equation is like a recipe. So what I want to do right now is I want to give you my version of a pictorial recipe, and we're going to work our way through it. So my recipe here calls for 2 apples, one, two, and put it together with 1 banana, and then somehow magically you have banapple pie. I will say this: I in the royalty-free section, I could not find an apple pie, so this is a cherry pie, but you can use your imagination here. So, if I were just writing this out, wouldn't you be able to say for every 2 of these, we need 1 of these, and we'll get 1 of these? That's a ratio, right? So just like any ratio, if you know how many of one thing you have, right, and you know what the ratio is for something else, you can figure out the other thing, right? So if I told you, oh, by the way, I have 4 apples, and I were asking you, help me out here. How many bananas would I need, and how many banapple pie pieces would I get? Wouldn't you all be pretty okay with using the ratio 2 to 1 and saying, well, if I have 4 apples, wouldn't I need 2 bananas? And wouldn't I get 2 banapple pie? That sounds weird to say, but I'm going to keep on doing it because I'm committed to it. So this is a ratio just like any other, right? If this was an equation, we wouldn't have drawn these out. We would have actually had the coefficients would be written like this: 2, 1, 1, and then behind it we would say 2 apple plus 1 banana gives us 1, I'm not going to write that again, 1 banapple pie, right? But I want to remind you of how ratios work. Yes, this could be a 2 to 1 to 1 ratio, but couldn't we also say if we wanted to, well, I don't know, 2 dozen, right? The ratio, wouldn't it work with dozens as well? Couldn't I say for every 2 dozen apples, I need 1 dozen bananas, and I would get 1 dose, evidently, and wouldn't I get 1 dozen banapple pies? I mean, it makes sense, right? So the ratio 2 to 1 to 1 works with all kinds of things. In fact, and you probably see where I'm going to go with this, couldn't I also say, yeah, for every 2 moles of apples, I need 1 mole of banana, and I'll get 1 mole of banapple? So the key thing here is whenever we have our coefficients, I'm underlining them, I don't know why, because I think underlining helps learning. But if I have, this is my equation, let's say this right here, and let me do this in a different color because again, that is proven to help learning. So let's say this right here was my overall equation, right? This is what I was working with. This is my overall equation. 2 apples, and let's pretend this was not apple, it was some compound. Wouldn't this be a 2 to 1 to 1 ratio? Agree? So let's actually try it with a real live problem. So I'm going to use this one right here, and let's use just for funsies, let's change our color to a more subtle blue. And I want to take a look at this. And again, I was deliberate in picking some kind of ugliness here, but I want to underline the things that really matter to us in this equation. The 3, the 2, the 3, and then the 2. And if I were reading a sentence about this, couldn't I say that 3 magnesium react with 2 aluminum chlorides to form 3 magnesium chlorides and 2 aluminums? That's the story of this equation. By the way, this arrow, we sometimes say it means yields. Yeah? So similarly, again, I don't want to insult your intelligence here, but couldn't we say 3 dozen of these for every 2 dozen of the aluminum chlorides will form 3 dozen magnesium chlorides and 2 dozen aluminums? But that's not really why we're here today, right? The reason we're here is because we're going to deal with moles. So let me just say it straight up. Equations are written in moles. What that means is when I'm actually reading this off, what I should be reading is this. When I take 3 moles of magnesium and react them with 2 moles of aluminum chloride, I will get 3 moles of magnesium chloride. I grew tired of writing the whole long way. And 2 moles of aluminum. Now this 3, 2, 3, 2 resonates with us, because if I have the coefficients in a balanced equation, if I tell you how many moles I have of any of these things, I can figure out how many moles of everything else I have as well. These here, this right here is a 3 to 2 ratio. Now, these ratios have a special name. We call them mole ratios. And I know that is super clever because they are the ratio of the moles of each of these things. The other thing I want to bear in mind, is this. This right here, this is a recipe. It doesn't mean we actually have that. That means this right here that I'm circling right here, and by circle I mean a large rectangle. This right here says that we have a recipe that requires 3 moles of magnesium for every 2 moles of aluminum chloride. Just like when you're going back up to our previous example, let's say that my recipe called for 2 apples and 1 banana. Well, just having the recipe doesn't mean that you have 2 apples and 1 banana. What if you have 10 apples? And what if you have 50 bananas? The recipe just tells you the ratio that you need to use with them. And that's going to become important as we go through this a little bit farther. Now, your takeaway from all of this should be simply this. The coefficients in a reaction can be used as mole ratios. That is, I'm going to put another M there, mole ratios. That is the takeaway from what we've just said so far. Now, let's move forward here a little bit. And it's incredibly important, enough for me to like pause and even use a different color, because again, different colors help us learn. That whenever you're doing any problem with an equation, you must have a balanced equation before you do anything in the problem. If you don't have a balanced equation, you cannot use the ratios, because the number that we just did right here, this 3, 2, 3, 2, if you didn't balance this beforehand, you'd have 1, 1, 1, 1, and that is not the recipe that you need to put together. Now, from the balanced equation, you can come up with a mole ratio, which is just a conversion factor that relates to the number of moles of any 2 substances in a chemical reaction. So the mole ratio is simply just the ratio between 2 different coefficients. Now, how do we apply this? Well, let's actually do a problem, because the best way to do stuff like this is to do a problem. And so let's take this example right here. We are going to have 2 aluminum, the actual recipe or the balanced equation. I was gentle and I gave you the balanced equation to start with here. I have 2 moles of aluminum oxide, and when they decompose, that's what this little arrow says right here, we're going to end up with 4 moles of aluminum and 3 moles of O2. Again, if you notice, I was very subtle there, but I used moles over and over again because these coefficients, they are moles. So if I start you off in a problem and I say, given 6 moles of aluminum oxide, and by the way, aluminum oxide, if you're looking at the things here, and you're like, I don't know what aluminum oxide is. Well, take a look at the equation. It can't be Al, because that's aluminum. It can't be O2, because that's oxygen. By default, isn't it this guy right here? You can say yes. I won't hear you, but I'll pretend like I did. So as with any problem, if I start you off with 6 moles of aluminum oxide, I'm going to write it as Al2O3. We're going to start us off by putting that into our little table of death. Now, where are we trying to go in this problem? They want us to know, if I have 6 moles of aluminum oxide, how many moles of aluminum? We'll call that question A. And then for B, they want to know how many moles of oxygen are there. Well, let's take a look at the ratios here, because see how we have 2 in front of the Al2O3 and 4 in front of the Al? So essentially, we can do this. We can write 2 moles of Al2O3 on top of 4 moles of Al, or we can write 4 moles of Al on top of 2 moles of Al2O3. Because that's equal to 1, because they're equivalent to each other. Now, let me remind you, like we've done in the past, we always want to, and I'm going to change color again because, as I said, it's super helpful for learning. Let's go green here, shall we? We have moles of aluminum, and here's what's really important, because some of you guys don't like writing units in. If you just write 6 up here, you're going to be in big trouble, because we want to go from Al2O3 to Al, and the ratio is 2 moles of Al2O3 for every 4 moles of Al. So we've got to determine where do we put the moles of Al2O3. So we're going to have to use one of these two right here. If you take a look at this one right here, you see how we have the Al2O3 on the bottom? So that's what we're going to do over here. We're going to put 2 moles of Al2O3 on the bottom, and we're going to put 4 moles of Al on the top. And that's going to allow us to cancel out the moles of Al2O3. And now the unit that we're looking for, and this is, let's say this is part A, because that's what we're doing here. We're just going to do the math. We're going to go 6 times 4 is 24, because we're multiplying whenever we have a line like this. And we're going to divide it by 2, and that's going to give us 12 moles of aluminum. Similarly, the part B said, well, what if they wanted us to go to oxygen instead? Well, same problem. We're starting with 6 moles of aluminum oxide, and we want to go to oxygen in this case. But now the ratio, if you take a look, isn't it 2 to 3? So I'm going to put the 2 moles of aluminum oxide on the bottom, and I'm going to put the 3 moles of oxygen on the top. And when I do the math on that, this is going to be 6 times 3 is 18 divided by 2. Wouldn't that give us 9 moles of oxygen? Now, I know that you're probably saying to yourself, oh, come on, man, I could have done this in my head. Yeah, you could have, because I chose 6, and that's an easy multiple of 3 times what these all are, right? So you could have just, with 6 moles of this, couldn't you figure out, yeah, I need to have 12 of this and 9 of this? You could have. But what if it wasn't 6? What if it was like 1.937? It wouldn't be quite as easy, right? And then what if it wasn't moles at all I gave you? What if I gave you instead, oh, I don't know, grams? Now, if you see the connection here, we're connecting back to the problems that we did in the previous videos. Didn't we use our periodic table a while back? And I'm going to very quickly scroll back to the nearest periodic table, which is right here. Didn't we say that the number that's underneath here, this number, isn't that the number of grams per mole? Which means that we can immediately use our periodic tables to do conversions between grams and moles. So if they don't give us moles in a problem to start off with, they give us grams, no biggie, man. We can simply convert to moles. So in this part here, it's really important. Since all of our equations are written in moles, and I did this little underlining thing right here, that means that whenever we are doing a problem, we have to convert to moles regardless of the unit they start us off. And how do we do that? Well, we use molar mass. If you're having trouble remembering from the last video, molar mass is, again, the number that we get from the periodic table. So if I was looking at carbon, and I looked in the periodic table, the number underneath is 12.01, and that is the number of grams per mole of carbon. So this would be the conversion that we could use if we knew either our moles or our grams. And if they start us with grams, we can convert to moles. Now, no video would be complete if we didn't try and do a problem, but if you take a look at the next page here, this is kind of reminding us just of some of the basic stuff here. The molar mass, if you take a look at aluminum, you can look at it on the periodic table and it would be 27 grams per mole. Or if we deal with a compound, this is one of the things you did in your last video, if I have CO2 right here, I could take the molar mass of carbon, which is 12.01, and I could take the molar mass of oxygen, which is 16.02, but since it's CO2, let me point that out to you there, we have to multiply that by 2, and when we add it up, we could get the overall molar mass of CO2 as 44.01. Why is that important? Because in problems, we're not always going to be dealing with individual atoms. So I'm hoping that at this point, we know that if we're given grams or even atoms, we can convert to moles, and that's what we need to do if we want to solve a problem. So let's try a problem that starts with grams of something. And that's a terrible circle. Let me try a different color pen yet again. So in this problem, they're starting us off with 72.0 grams of O2. And they're asking us, they tell you that there's a crazy amount of H2, which essentially says we don't really need to worry about H2. They're asking how much water could be formed in moles. Now, I want to point out something to you here. If you just jump into your problem and you're like, all right, I'm going to start off with my 72.0 grams because that's what they're starting us off with and that's what we put in our table, you would have escaped the most important thing. You must have a balanced equation. I'm going to write it up here with a question mark. Do we have a balanced equation in this problem? Well, let's take a look. Don't we have two hydrogens right here and two hydrogens right here? Check mark. But oh no, here we have two oxygens and we only have one oxygen here. I didn't leave a whole bunch of space here, so I'm just going to put it in here. So wouldn't we have to put a 2 right here? But when we put a 2 right here, doesn't that also change the number of hydrogens? So wouldn't we have to put a 2 right here? So now our equation says 2H2 plus O2 goes to 2H2O. But again, don't we write everything and read everything in moles? So shouldn't we really say for every 2 moles of H2 that react with 1 mole of O2, we'll get 2 moles of H2O? But here's what we're starting with here. Aren't we starting with grams of O2? Well, this is not a gram ratio. If you look at this, you cannot say, I'm going to put a circle through it and a line that reminds you cannot use grams. You can't say 1 gram of O2 will form 2 grams of H2O. This is not a gram ratio. It's only a mole ratio. So what's our first step? Well, if we have grams, we've got to convert it to moles. So how do we do that? Well, if you look on the periodic table, and I'm not going to scroll all the way back up to the top, the molar mass of one single oxygen is equal to 16.00. Well, don't I have 2 oxygens right here? So couldn't I go 2 oxygens, wouldn't that be equal, that looks like 20, wouldn't that be equal to 2 times 16.00? And if I did that, wouldn't that be equal to 32.00? That would be the number of grams per mole. And I want you to be careful here because, again, this oxygen is actually a diatomic molecule. Remember Brinkelhoff? That's how they exist. So how do I put 32.00 grams per mole of O2 into an equation? Well, I have to put the grams opposite. And remember, I can always put the grams or the moles on top or bottom. And this is reminding you back to how we did conversions back in the day. Couldn't I go 32.00 grams of O2 on the bottom and 1 mole of O2 on the top? And when I do that, couldn't I do the math on this? And wouldn't that give me 2 moles of O2 if I stopped right here, right? But here's the thing. If I stop right here, would I know the number of moles that I have? But couldn't we go one step farther and couldn't we say for every 1 mole of O2, isn't there 2 moles of H2O? Because that's the coefficient in front of each one. So if we're doing that, we could then go like this. Couldn't we go 1 mole of O2 on the bottom and 2 moles of H2O on the top? Now I wish I hadn't written all the stuff here, but if we didn't do the math, 72 divided by 32, that's 2, right? Oh, except that's not 2. I'm going to change this problem on the fly because I want this to work out really, really smoothly. So I know that I'm not legitimately allowed to do this, but you know, math. I'm going to make changes to 64.0 grams just because I don't want to pull up my calculator, and this is going to be 64.0. For those of you that don't have magical erasy things like I do right now, I am really sorry. I invite you to do a line through this number just like I did. So if I start off with 64, I know this is a terrible way to teach, but I don't want to have to go back and do some math and take even more time than I'm doing right now explaining this. But if I go 64 divided by 32, wouldn't that give me 2? And then 2 times 2, wouldn't that give me 4? So wouldn't I have 4 moles of H2O altogether? Now, I want to point out something to you here. This is actually not going to give me full points in a problem because if I take a look at this, don't I have in the problem 3 significant figures to start off with? And if I have 3 significant figures here to start off with, and I'm using 4 significant figures right here, these coefficients here, the mole ratios, they have infinite number of significant figures. So the reality is I needed to have 3 significant figures in my answer, and I should have written it as this, 4.00 moles of H2O. Now, I want you to maybe, if you're having a little bit of trouble with any of this, kind of look back through this video. But we clearly are going to go over this, and we're clearly going to be practicing this in class. But I need you to go over this and do your very best to understand it prior to me going over it in class. And I need you to go into the summaries and make sure that you are writing out the things that you're having questions on so that I can help you in class with that as well. Hope you're having a blessed day. Stay safe. God bless, and I will see you soon.